Hi there. In this video, we're going to be talking about how to find the maxima or minima of a function of two variables. These maxima and minima are the plural forms of the words maximum and minimum. So the points on a surface where it is the highest and the points on a surface where it is the lowest. So we'll be looking at functions of two variables. And so let's go ahead and take a look at this one right here. All right, so we can see this one has a maximum and it also has a minimum. So we're going to try to explore how to find exactly where this maximum and minimum occur on a surface like this. So to get started, I want us to just think about what we did in single variable calculus. We had something called the second derivative test. And so we're going to have something similar for functions of two variables, but let's just remind ourselves how the second derivative test worked. Okay, so here we have a single variable function, something that you studied in Calculus 1. And we want to know how to find the maximum and minimum points. Well, we see we have a local max right over here. Oh, my contrast is up high. Local max right over here, local min over here. How do we identify where these things are? Well, the trick was to look at the tangent line. And of course, we can get the slope of the tangent line by just computing a derivative. So if we look at where that maximum happens, we see that something very special happens with the tangent line. The slope becomes 0. In other words, the tangent line becomes horizontal. So we know that when we look for maxes or mins, that's where we're going to look. Now, we also know that we have to be a little bit careful here. We have to be a little bit careful because just because the tangent line becomes horizontal doesn't mean we have a max or a min, as is the case here with this function f of x equals x cubed. So it's not enough to see where the slope of the tangent line or where the derivative is 0. We have to test one other thing. And one thing that we can check is the second derivative. And that brings us to the second derivative test. The second derivative test says first look where the derivative is 0. Okay, so you're going to find points like this. And then check the second derivative. If the second derivative is positive, we know we have a local minimum. If the second derivative is negative, we know we have a local max. In this particular case, the function that we're looking at here, the second derivative is 0, and so we have neither. If we go back to the other function I had here, I think it was something like x minus x cubed. Yep, that was it. If I find these points where the first derivative is 0, it's snapping to that point, but right around there, you can see, there it is. I could find this point by checking where the first derivative is 0, just solving a simple equation. And here I can see that the second derivative is negative, and so I know, just from that analytical computation, that I have a local max. And similarly, if I find this point over here, the other point where the derivative is 0, we see that the function is concave up, and so the second derivative, if I were to compute it, I'd see that it was positive, and so I know I have a local minimum. Okay, so back to our function of two variables. What kind of test do we have here? How are we going to determine whether we have local maxes or local mins? How are we going to find these? Well, we have the second derivative test for such functions. So we need to have a function of two variables for which the first and second order partial derivatives are continuous. All right, so it needs to be continuous where we're going to find the local mins and local maxes. Now, if the first partial derivatives are both equal to 0, in other words, if the gradient vector is equal to 0, that's another way to phrase this problem, then we check this special quantity called the discriminant, and it's denoted by capital D. And it's computed by taking the second x derivative of the function multiplied by the second y derivative of the function, and then subtract the xy derivative of the function squared. Once you compute that discriminant, we're going to check to see if it's positive or negative. If it's positive, then we will have a local max or a local min. How do we determine which one it is? Well, then we check the second x derivative of the function. If the second x derivative is positive, then we're in the situation where we're concave up, and so we have a local min. If the second x derivative is negative, then we're concave down, and we're in the situation where we have a local max. Now, it doesn't need to be the x derivative. We could have done the y derivative. All right, so it could be the second y derivative we check instead. All right, but you only need to check one or the other. All right. Now, that's the situation where the discriminant is positive. Now, if the discriminant is negative, then we know that we actually have neither a max nor a min. We have what's called a saddle point, and we'll discuss this later in the video. If the discriminant is equal to 0, then the test is inconclusive. We don't know what we have. We have to do some other investigation to find out. This is similar to the situation where we had, let's see if I can find it here. Yeah, this is similar to the situation where we just had this going on, where when we did the first derivative test, the second derivative test for a single variable function, and we found a critical point where the first derivative was 0, but we didn't have enough information to say whether it's a local max or local min. This is the analogous situation here. If the discriminant is 0, we're in this kind of situation. We don't really know what it is. It could be one, it could be the other. We need to do some more analysis to figure out what's going on. All right, so let's study this function. Let's take a look at it. We'll write it down, and we'll do some analysis, and we'll figure out. We'll use this second derivative test, and we'll figure out what's going on exactly. Okay, so here we are. We are going to use the second derivative test to find those local maxes and local mins that we saw in the picture. Okay, so to do that, we need to compute the derivatives of the function up to the second order. So let's start with the first order derivatives. Let's start with fx. Now, I'm not going to write the parentheses xy here. I'm just going to abbreviate it, just write it fx. Okay, so let's see what this equals. All right, so let me do it on a separate piece of paper, and then we'll compress our work and just write our result over there. So let's see. We use the quotient rule, right? So it's going to be this, and then when we simplify this, what do we get? And I think I can pull out a factor of -4 here. So there we go. That's what that simplifies to. So let's go ahead and just write that in next to fx. Okay, so now let's compute fy. All right, so what does fy equal? Okay, so again, we'll use the quotient rule. Let me do this on a separate sheet, and then we'll write it in after we do all that messy work. Okay, so that's it. So we'll just write that in next to fy. Okay, so those are the first derivatives. Now these are what we need to identify where the local min might occur. Okay, so what we're going to do is we're going to see where are these equal to 0. So these will be the critical points. Okay, so I think the easiest one to look at first is fy. Let's see where fy equals 0. Well, if fy equals 0, the only way that can happen is if the numerator is 0. The numerator can be 0 only if x is 0 or y is 0. Okay, so x equals 0 or y equals 0. Okay, so we need one of those to be true. Now let's look at where fx is equal to 0. So fx equals 0, well that will only happen if the numerator is equal to 0 again. I mean the denominator can't make a fraction 0, so we only need this part to be equal to 0. So we're just looking to see where this is true. Okay, let's consider these together. If x is equal to 0, then what does this become? This expression becomes this one, right? Can this ever be true? Well, no, because this is always less than or equal to 0, and then we're subtracting 1 from it. So it can't be equal to 0. That's impossible. So there are no solutions here. Okay, so that leaves only this other condition, y is equal to 0. So let's check that one out. Well, if y is equal to 0, then what does this become? We get this equation. This has solutions, right? This has two solutions. X equals plus or minus 1. Okay, so this is our solutions, our critical points, where x is equal to plus or minus 1 and y is 0. So those are two different points. So there they are. Those are the two critical points, where x is equal to plus or minus 1 and y is equal to 0. So this is where we need to do the second derivative test. We need to investigate the discriminant at these 2 points. Now, to get the discriminant, we're going to need the second order partial derivatives. So let's compute those. Okay, so here's our function, here's fx. Let's compute fxx, the second derivative with respect to x. So I'm going to use the quotient rule on this. So let's go through that. Okay, now one thing we should observe is that this term x squared plus y squared plus 1 appears as a factor of the numerator. It appears in each term. So that means we can cancel it with one of the factors in the denominator. So that reduces the number of factors in the denominator to 3. It reduces that one to just 1, so that's just an exponent of 1 now. And it kills this term over here. So let's simplify this. Okay, I see here we have some like terms that we can combine, right? So let's combine those. Okay, and at this point, I think we can factor out a negative 2x from the numerator. So let's do that. And there we have it. There's our expression for fxx. So let's write that down below fx. Sorry, I meant to the right of fxx. There's no room below it. I've got fxy down. I got fy down there. All right. So now let's compute fyy. And again, we'll just use the quotient rule here. And again, just like we did before, we observed that x squared plus y squared plus 1 is a factor of the numerator and the denominator, so we can cancel it out here. Right? And let's simplify. And I see I can combine some like terms here, so let's do that. And I see that 8x is a factor, so let's factor that out. Okay, so there's our expression for fyy. Let's write that off to the right of fy so we can consolidate everything. And now we just have one more derivative to compute. We need to compute fxy. So let's see what that one equals. Okay, so to compute fxy, I'm going to use Clairaut's theorem. Clairaut's theorem says that fxy is going to be the same thing as fyx. Why do I want to use that? Well, because I think this function, fy, is going to be a little bit easier to differentiate than fx. So I'd rather differentiate this with respect to x than this with respect to y. So let's go ahead and do that, okay? So we'll just look at fy and differentiate that with respect to x. All right, so I'll use the quotient rule here. And like before, we see that x squared plus y squared plus 1 is a factor, so we can cancel it out here, here, and here. Okay, so let's simplify what we have here. All right, and I see we have some like terms we can combine in the numerator. And I think we can factor out a negative 8y. So let's do that. Okay, so here we have fxy. Let's go write that in up above. Okay, so now we have these 3 ingredients that we need to write down the discriminant. Remember, the discriminant is given by this expression. Okay, so one thing you could do is you could just dive in, plug these things in here, and simplify. Write it out. See what you get. I wouldn't recommend that. I think that's going to get really messy and really ugly and going to be hard to simplify. So if you think a little bit about what we actually have to do here, we need to test the discriminant at the critical numbers. So here's what I would do. I would simply evaluate the discriminant at the two critical numbers we had. 1, 0 and -1, 0. So we just need to evaluate this at those points. All right, so what's f(x)(x) at 1, 0? So I'm going to plug in 1 for x and 0 for y. What do I get here? Well, if you compute that out, you'll see that this whole thing just simplifies to the number 2. All right, so that just becomes 2. What about fyy? What if I plug in 1, 0 for x and y? Go ahead and plug that in and check it out. You'll see that that, again, simplifies to 2. All right, what about fxy? If I plug in 1 for x and 0 for y, well, look, the whole thing's being multiplied by y, so if I plug in 0 for y, I get 0. So what do I get here? I get 4. Now, I don't really care what exactly the number is. All I care is that it's positive. Okay, now let's check out -1, 0. Let's plug -1, 0 into fxx up here. What do you get? Well, you get -2. Now let's plug -1, 0 into fyy. What do you get? Again, you get -2. And if you plug it in to fxy over here, well, again, if y is 0, then this whole thing is 0. So you get 0. And we get +4. The important thing is that it's greater than 0. Okay, so this is all we need to do to determine, what kind of critical points these are, right? Because here the discriminant is positive at 1, 0. So that means it's either going to be a local min or a local max. To determine which one it is, we just evaluate fxx or fyy, whichever one's your favorite, at that number, right? And we actually said above that it's equal to 2. Well, that's positive. And so that means that that's kind of like being concave up, so that means that it's a local minimum. So there's a local min at the point 1, 0. And then we check this one. We know it's a local min or a local max because the discriminant is positive. So now we just check fxx at that number. Or, like I said, you could do fyy, doesn't matter. And we see that it's -2, right? We computed that before. That's negative. And so that tells us that it's concave down, right? So that means there's a local max. Okay, so let's just go see if this corresponds to what we were seeing. All right, so here we are. Let's see if what we just found is what we're seeing here. We said that there was a local minimum at the point 1, 0. Well, if you look at that, right, here's x equals 1, right, and y is 0. If I tilt this thing up from the top, you can say, yep, that's exactly where this minimum point is. That's exactly that little dip right there. And then we said there was a local max at -1, 0. So if I go -1 in the x direction, let's go right over there, -1, and we'll go, well, y is 0, so we're just above that point there. Yep, that's where the max is, right there, at -1, 0, right there. And so we have successfully identified these maxes and mins. You don't even need to see the graph if we use the second derivative test. Okay, I just want to show you one other possibility that you can run into here. Let's look at a different graph. All right, we have this saddle shape. Looks like a saddle, right? And this is given by the expression 1/4 x squared minus y squared. All right. Now, I just want to check out what happens here when we run the second derivative test on this guy. Okay, so let's go down and take a look. All right, so what I'm going to do is I'm going to compute fx and fy. There's fx, pretty easy to do. How about fy? Okay. So now I think we can find the critical numbers. The critical numbers are where these are going to be both equal to 0. Oh, I should say critical points. I'm used to Calc 1. Here we're looking for points, critical points. We're looking for where fx is equal to fy is equal to 0. Well, I think I can see that that can only happen when x and y are both 0. So the only critical point is this one, 0, 0. Okay, now let's try to identify what kind of critical point that is. So we're going to do the second derivative test. We need to compute the discriminant. And for that, we need to find the second derivatives of f. So let's compute fxx. Well, that's just 1/2. That's pretty easy. Let's compute fyy. Well, that's just negative 1/2. Let's compute fxy. Well, I'm just differentiating this with respect to y. Well, x is a constant with respect to y, so this is 0. Okay, so we can compute the discriminant. The discriminant is given by, remember, fxx, fyy, minus fxy squared. This one, I think we can just compute the expression and simplify it, because these expressions are simple enough. So fxx times fyy is 1/2 times negative 1/2, so that's negative 1/4. Minus 0 squared. So the discriminant is negative 1/4. Now here we see that the discriminant is negative. Now remember from the second derivative test what that means. That means that we have a saddle point. And that's exactly what we were seeing in the graph. So that's neither a local min nor a local max. We can stop right here. Let's go back and take a look at the graph. And yeah, so I mean, we observed it was a saddle to begin with. And so we found that this point at 0, 0 here, this point right here, is a critical point, but it doesn't correspond to a min, nor does it correspond to a max. And we can see that just by looking at the discriminant. All right, so that's just an example of something you need to be prepared for when you run the second derivative test.